Okay, Physics 12, we're going to continue with our work in our unit on electricity and electromagnetism and electric fields, and today we're focusing specifically on the electric fields, right? So our last lesson we were just kind of talking about like the electric forces between objects, right? And now we're going to be specifically talking about the electric field that an object can create and how that kind of plays into our unit. Okay, so let's get into that. So there's going to be kind of part one, part two. They're both on electric fields, but again, we're trying to cover as much material as possible. So again, it might be a bit of a longer video, but it kind of covers all of the stuff on the same topic, right? Similar to last time where it was like, oh, here's the basics. Everything just kind of in straight 2 dimensions and or just like on a 1-dimensional scale. And then all of a sudden it's like, okay, well, let's step it up a notch. And now we're going to deal with vector components again. All right, so that's just kind of how it's going to work out. So we start with electric fields, right? So when we talk about fields in general, right, the fundamental concept is that a field is a property of space, okay? So an object is able to influence the space around it, and it sets up either an electric field, a gravitational field, or a magnetic field. We're specifically going to be talking about electric and gravitational fields, mainly electric in this lesson. We're going to leave magnetic fields until we get closer to the section on magnetism, okay? But the object producing the field, right, whether it be electric, gravitational, or magnetic, is called the source. And this field in turn exerts a force on other objects located within it, like around, objects that enter its field, okay? So like in terms of gravity, right, force of gravity is like the planet itself, right? The bigger planet would be the source of the field, and then it has a gravitational pull, and anything that enters its field is acted on by that source object, okay? So in terms of like the electricity aspect of it, if we're going to talk about other things entering the field, we can talk about something that's called a test charge, okay? And this test charge is a point charge, so it's just like a single kind of point in space that has obviously it has a charge and it has a magnitude, but the magnitude is so much smaller than the source charge of where the actual field comes from that any field generated by the test charge itself is negligible in relation to the field generated by the source charge, okay? So in a situation like that, we're not thinking about fields interacting with each other, it's just the field of the source particle acting on the test charge, because we're talking about a test charge that's so much smaller that like this says that its own field would be negligible compared to the field that it's actually in from the source, okay? So we'll be kind of talking about like source charges and then the test charges, okay? So when we talk about electric field intensity, okay, so the intensity of a field that surrounds an object is directly related to the force acting on the charge and the magnitude of the charge itself, okay? So again, as we kind of work through this, we also have to remember about positive and negative symbols being used to explain the charge acting on a specific object, right? So charges are always going to have a positive or a negative component with them. In our calculations, we don't really worry about them. We just kind of think about the magnitude of it, and then we can kind of identify what's going on with the charges in terms of either repelling or attracting afterwards, okay? Now, when we talk about drawing kind of field intensity and field lines, standard practice from physicists, right, is that the direction of the field strength corresponds to the direction of the force exerted on a positive charge, okay? So because you can have 2 different types of charges, they've kind of had to adopt like okay, this is the convention we're going to use so there's no confusion. So that convention is that your field strength is corresponding to the direction of the force exerted on a positive charge. Okay, so you're going to be thinking about, well, what's the positive charge doing? And then if it's something on a negative charge, it'll be the opposite, and we'll get into that in our questions, okay? So how we actually calculate the electric field intensity, okay? Like I said, it's a relationship between the force and the charge, okay? So the magnitude of the electric field can be calculated by using the following formula, okay? So your electric field intensity is going to equal the electric force divided by the electric charge, okay? So your units for electric field intensity are newtons per coulomb. It doesn't have its own thing. That is just what the unit is, okay? And again, this calculates our magnitude of our electric field. And then again, in terms of direction, right, it is still a vector quantity. In terms of direction, it's going to be in relation to how this force is acting on a positive charge, right? So if the force is acting on a positive charge to the right, then this electric field will also be to the right, right? If this force is acting on a positive charge to the left, then this will go to the left, right? However, if this was a force being acted on a negative charge to the right, right, then all of a sudden this becomes electric field intensity to the left, okay, because it's based on the positive charge, all right? So just keep that in mind. All right, so let's just kind of go through some sample problems. So we start off with this one, just a quick little demonstration of the formula. So what you have is a positive test charge, so this would be the one that's in the field itself, is placed in an electric field, and it experiences a force of 4.0 times 10 to the minus 9 newtons west, okay? So the first thing we're being asked here is what is the electric field intensity at the location of the test charge? All right, so again, what we have is we have the charge of that test charge, okay, and we also have the force that it's experiencing. And again, what I want you to notice is that this was a positive charge and it's experiencing a force in the western direction. So because this was a positive charge experiencing a force to the west, the electric field intensity will also be to the west. Okay, so let's solve that one though, just using that quick formula. Okay, so right, our formula that we had was that our electric field intensity was equal to the force divided by the actual charge. Okay, so all we really need to do here is plug and shove, right? We've been given that the force that it's experiencing is 4.0 times 10 to the negative 9 newtons, and we know that the charge is 2.0 times 10 to the negative 9 coulombs, and that's just a quick little division, and it's 2.0 newtons per coulomb. And again, like I mentioned, the direction of this is going to be west because that was the direction of the force on the positive charge. Okay, so they correspond to each other. So because that force was applied to a positive charge and it was going west, then the field intensity is also west. Okay, so let's look at part B then. So part B is predict the force that would be experienced by a charge of Q equals plus 9.0 times 10 to the minus 6 if it replaced the test charge QT. Okay, so if we have a different test charge that's coming in to this field, what force would it experience? Okay, so again, we're assuming it's coming into the same field. The field intensity isn't changing here, right? So for solving this one, right, we already have that our field intensity that we solved from part A was 2.0 newtons per coulomb, right, acting in a western direction. Our new test charge value that we've been given is that plus 9.0 times 10 to the minus 6 coulombs, and we've been asked, well, what force is that particular charge going to experience? All right, so it's just a rearrangement of that formula, which was the intensity, which is equal to the force, divided by the charge, and I'm looking for force, so I just multiplied both sides by charge, right? So the field intensity multiplied by the charge, the test charge, so that sometimes you get the T, that's going to equal the force. So that's just a matter of taking our 2.0 newtons per coulomb and multiplying it by our charge of 9.0 times 10 to the minus 6 coulombs. The coulombs will cancel, and that will give us a force in newtons, and you'll just get 1.8 times 10 to the minus 5 newtons. Okay, and again, in terms of direction, right, the electric field intensity was moving to the west, meaning it acts on a positive charge to the west. Since this is a positive charge, this force will also be to the west. Okay, so there's our answer for part B. Okay, carrying on. All right, so again, those are your solutions. Okay, so briefly we can kind of talk about gravitational field intensity here as well. I'm not going to focus so much on the gravity part because we've spent a lot of time with gravitational forces in fields, but it is kind of in the same topic, so we do kind of need to mention it. So again, if we talk about gravitational field intensity, it's the amount of force exerted on each unit of mass of an object at a point in space caused by the presence of another object. right? And then space includes a region on or near to the surface of the planet, right? And we've seen this kind of before. We've already explored this. The big difference here with gravitational fields is that there's not kind of two different directions, positives and negatives. It's everything is being drawn to the bigger planet, right? In terms of drawing kind of your field vectors of like where it's being pulled to, they're all being pulled to the main planet, okay? But you'll notice that, I think we've seen this formula before, right, where the gravitational field intensity at a point is the quotient of the gravitational force and the magnitude of the test object's mass, right? So it's different than the electric one. The electric one was, again, the force divided by the charge, okay? But with gravitational field intensity, it's the force divided by the mass, okay? So very similar, okay? And again, you get this would be considered the gravitational field intensity. This is the gravitational force measured in newtons, and this is the mass itself, right? Now, we've always kind of calculated Fg by, obviously it's m times g, just a rearrangement of that formula, right? And if it was on Earth, we already knew what the gravitational field intensity was. But if we're dealing with something else, we would need to know, like if we're solving for that value of g, we need to know what force is exerted on a particular mass to figure out what that intensity is, okay? So this would be kind of a sample problem to deal with here, right? So if you have a mass of 4.60 kilograms placed 6.37 times 10 to the 6 meters from the center of a planet, and it experiences a gravitational force of attraction of 45.1 newtons, what is the gravitational field intensity at this location? And then discuss the significance of your answer. So if we look at that one, right, so this was number 2. So the values that we had there is we were given that the mass of this particular object was 4.60 kilograms. We were given that it was placed 6.37 times 10 to the 6 meters away from the center, and we were given that the force that it experienced is 45.1 newtons, okay? We're asked to find G, right? What's the gravitational field intensity? And for this one, we actually don't need this value of the radius at all. Not for this particular question, because we have this value here, okay? So you might remember other work that we did with gravitational stuff. We would be able to use the radius because we didn't actually have the force, right? But in this case, if you have the force, it's just a simple little calculation of, all right, it's the force divided by the mass. So it's the 45.1 newtons divided by the 4.60 kilograms. And when you do that, you get a value of 9.8 newtons per kilogram. And then again, if you remember your definition of Newton, right, being kilograms times meters per second squared, your kilograms cancel, right? And then you end up just getting 9.8 meters per second squared. So this gravitational field intensity, right, the significance of that is that the planet is likely Earth, right? Because this is what we know the gravitational field intensity of Earth is. So there we go, okay? All right, moving on. Okay, so like I said, that was just kind of the intro part, right? So if you want just a few little practice problems, stop here maybe. Make sure you're good with just those basic equations, right? Nothing too crazy, simple equations. The biggest thing is probably just getting a handle on the direction of the field intensities or the forces, right? So just when it comes to the electric field, right, really got to remember that it's those forces acting on positive charges, right? So if it's a negative charge, you need to switch it. Okay, so just those are some practice questions you can take a look at, right? These are the actual pages in your textbook. I don't think I've been updating those properly, sorry. But these are the actual pages in your textbook. But I have also attached the PDF documents just of those pages in case you don't have your textbook, okay? They're the same numbers though. All right, so those are ones you can take a look at. So feel free if you want to pause and take a look at those now, by all means. If you think, I'm good, I'll do them all at the end, that's fine too, do you. All right, but we're going to continue on with our next little section. All right, so this would be electric field part 2. Okay, so obviously when we talked about the electric field's strength calculation, the intensity, it was that force divided by the charge, right? And that's just really a general definition because sometimes you don't have the force, right? You don't know the force that's being applied to that charge or what force that charge is experiencing. All you really know is how far away it is from the source charge, right? So what, right, so that general definition is kind of doing it without distance, right? However, if we're considering that point charge, right, a single charge occupying a minute region, we also need to kind of consider distance, right? And this allows us to determine specific field strengths by observing a single point charge within a much larger field. Okay, so the distance is quite helpful. So again, reminder once again that electric field's direction is traditionally determined based on the direction in which a positive test charge would move if introduced to that particular field. Okay, so if the field pushes a positive test charge to the east, it would mean that if a negative test charge was placed in that field, it would move it to the west. Okay, if a field would move a positive test charge south, that would mean that if you placed a negative test charge in there, it would move it north. Okay, so just keep that in mind. Okay, so that direction of the field is radially outward from a positive point charge, okay, and radially inward toward a negative point charge, right? So if you see a positive point charge, you're kind of pointing away from it, whereas if it's a negative one, you're pointing towards it, okay? All right, so this kind of gives us a different formula for the electric field intensity, okay, from one that we had before. So I'm just going to do a quick little derivation here to show you where this one comes from. It's really, really easy. So this was what we had, right? This is what I introduced to you just a few minutes ago, right? Where that field intensity is equal to that force divided by the charge, okay? The test charge specifically. Now you might recall from the last lesson that we also had an equation for electric force as that constant multiplied by the product of the two charges, right, the source charge and the test charge, right, divided by the distance between them squared. Now, if we take that and substitute it in here, right, we get, right, K, the charge of the source, charge of the test, divided by R squared, and then also divided by the test charge again, right? And then what you notice is, oh, how convenient, these will cancel, right? And then what you get is the formula that was on the board there, or on the slide, sorry, right? EQ over R squared, right? And you notice that the Q that was remaining was the source charge, not the test charge, right? So again, this is one of those a slightly different formula that allows us to still find the electric field intensity if we don't know certain things, right? So if we didn't know the charge of the test charge, or if we didn't know the force that it's experiencing, right, we can instead still find the electric field intensity from just knowing the source charge and the distance between a particular point charge placed in the field, okay? Similarly, if you wanted to kind of think about it, this kind of comes from Millikan's oil drop experiment, where there's a relationship between an electric charge, electric field intensity, and actually gravitational field intensity as well. Less commonly used, but still worth just at least mentioning here, kind of where are these things equal. In that, when your gravitational field intensity is equal to your electric field intensity, right, what you get is that idea of like mg is equal to QE, right? Just that's rearranging of both of those formulas for gravitational field intensity and electrical field intensity, right? And then just kind of setting those equal to each other, right? So again, it less commonly used, but it's still relevant to kind of have in there. All right, so let's just kind of go into some sample problems now using this new formula. So in this first one, we're being asked, what is the electric field intensity at a point 30 centimeters from the center of a small sphere that has a positive charge of 2.0 times 10 to the minus 6 coulombs. All right, so let's do that one. Okay, so with this one, where am I at? Okay, so again, we're using that new formula, right? So our electric field intensity, K times Q divided by R squared. Okay, we have that K was our Coulomb's constant, right? So that was 9.00 times 10 to the 9, right? And then you had, again, I'm just leaving out units for space, right? And then you had your charge, the source charge, and that was given to us as 2.0 times 10 to the minus 6, or that could have been given as 2 microcoulombs, right? Again, just don't worry about the positive or negative here, just put in the magnitude, okay? And then your radius should be in meters, so that would have that 30 centimeters would be 0.3 meters squared. Okay, so then once you calculate all of this, you end up getting a value of 2.0 times 10 to the 5 newtons per coulomb. Okay, so there's your electric field intensity. In terms of direction, right, because this is still a vector, right, if we kind of just quickly go back to the question and see what it's telling us, right, it's saying electric field intensity at a point that's distributed from the center of a small sphere that has a positive test charge of 2.0 times 10 to the minus 6. So since they're telling us that that small sphere was a positive charge, okay, that means that the field intensity is radiating out from that charge. Okay, so that means the field intensity has a magnitude of 2.0 times 10 to the power 5 newtons per coulomb, and in terms of direction here, all we can say is out of the positive charge, or pointing away, right? Right, so like pointing away from the sphere, okay? Because it was positive. If that was a negative charge, right, the magnitude would have been the same because we're just kind of using the absolute value here, but it would have been pointing in the other direction, right? So like if it's a negative source charge, right, the field intensity does this. Okay, so there's the difference. Okay, where are we at? Right. Okay, so let's take a look now where we amp things up a little bit and we start looking at, multiple charges acting on, a point and seeing kind of where all of our chips lie. Okay, so adding to this now, you've got 3 charges, A, B, and C. They're located at the corners of a square with sides that are 5 centimeters long. What is the electric field intensity at point D? Okay, so the diagram that's going to be nicer than mine has already been used here to kind of show you what's happening. Okay, but just to kind of walk us through this a little bit more here, this is what's going on. Okay, I'm just going to redraw and go from here. Okay, so yes, you've got A, D, this is B, and C. Okay, you know that each of these values is 5 centimeters. You have that this has a charge of plus 6 microcoulombs. This has a charge of also plus 6 microcoulombs. This has a charge of minus 5 microcoulombs. Okay, and we're being asked about, okay, well, what's the charge, right? What's the electric field intensity that's happening here? So remember, if these are positive, right, then our electric field is going to be radiating away from those charges, right? So if we're going to go away and to point D, right, we're going to have something that's going like this, okay? And from A, again, this is positive, so this is all going to be radiating outwards, and it's at point D, so we're interested in this, right? Now, this is a negative source charge, which means everything's going to be coming into this one, right? So from point D, right, in relation to point D, we're interested in this, okay? So that's why you're seeing that diagram there. Let me go back to it. Right? So you're seeing that there's 3 different forces acting here on D, right? So on D, you've got this, the charge from C, right? The field intensity from C is pulling it up, right? From A, pulling to the right, and from B, pulling it down and to the left, okay? So we're basically just trying to figure out, okay, well, what's the sum of all of those electric field intensities at that particular point, okay? So we go back to that, right? So I mean, this is kind of what's happening there. So if we just think about point D as a whole here, right? You've got this electric field intensity going up, right? You've got this electric field intensity going to the right, and this electric field intensity going down and to the left, okay? Now, because this is a square, we know this is a square, this is going to cut directly in a right angle, through the right angle, so we know that this is going to be a 45-degree angle, right? So if we think about this value here, this is a 45, okay? Only because we know it's a square, okay? So we've got three different field intensities that we're looking at. So this is the field intensity here of C acting on D, okay? This is the electric field intensity of A acting on D. Okay, and this is the electric field intensity of point B acting on D. Okay, so what we need to do, because this is in 2 dimensions again, we need to take a look at, all right, well, we got to do sum of vector components. Now, it's not going to be too bad because this only has an x component, this only has a y component, and what's nice about this 45-degree angle is that the x and y components will be equal, right? But we still need to figure each of these out. So away we go. We need to start looking at calculating each of these. So let's start with the electrical field intensity of C at D, okay? So we'll start that one. Right, so that was the point C acting on D, right? And again, remember that our formula there is constant multiplied by the source charge divided by the distance between them squared, right? So that value is going to equal that 9.0 times 10 to the 9 multiplied by our source charge, which was 6 times 10 to the minus 6, and then the radius between them, right? So here, the distance between C and D, I guess I should kind of redraw that again. Right? That distance was 5 centimeters for all of them. So in that sense, then this radius has to be in meters, so it's 0.05 squared. Okay? And then you multiply all that together, and you get a value of 2.16 times 10 to the 7 newtons per coulomb, and that's just going to be going straight up. Right? So if we're going to think of it that way, right? In terms of a y component just going straight up here. Okay, then we can do the same thing for the electric field intensity that A has at D. Okay, same idea, same formula. So it's still going to be that 9.0 times 10 to the 9 for our Coulomb's constant. The charge of D is, again, the same, 6.0 times 10 to the minus 6 microcoulombs. And then the distance between them again here is the 5 centimeters, so 0.05 squared, and lo and behold, you get the exact same answer, except its direction is to the right, okay? So it's part of the x component instead of part of the y component, okay? So got it here, got it here, we need this, okay? So now that we need that value, right, we can use that same formula, right, where we have Coulomb's constant, we have the charge of point B, right? What we need is the distance between them. And the distance between them has to be that shortest possible distance here, and that's just the diagonal of that square, right? So this is, if this is 5 centimeters and this is 5 centimeters, then you're just going to use Pythagorean theorem to find this distance, right? So 5 squared plus 5 squared is 50, and so this is going to be root 50, right? So that value of R is going to be root 50, which is about 7.07, and that was in centimeters, but we need it in meters, so again, this value of R is going to be 0.0707 meters, okay? So we go to find that electrical field intensity of B at D, right? It's that same, okay, Coulomb's constant, 9.0 times 10 to the 9, multiplied by the charge. I'm just going to get rid of this for now, I need the space, right? And the charge here was, it was minus 5 microcoulombs, so again, just use the magnitude, 5.0 times 10 to the minus 6 coulombs, divided by the distance, so this 0.0707 squared, okay, And then again, once you do that, you get this nice little value here. So this is the electric field intensity B at D, and you get a value of 9.0 times 10 to the 6 newtons per coulomb. And again, that was acting like that. Okay, so if we wanted to kind of give it a direction, we could call it 45 degrees south from the negative x-axis. We could just call it west 45 degrees south, which is what I'm going to call it right now, just because it's faster and less writing than 45 degrees, down from the negative x-axis, right? So in this case now, what we need then is the actual x and y components, right? So since we knew that that was a 45-degree angle because it cut directly across the diagonal of the square, it's just this multiplied cos 45 and this multiplied by sine 45. Beauty is sine 45 and cos 45 are the exact same thing, so what you're going to get is the exact same answer, right? So one's just going to be going left and one's going to be going down, right? So if we want to think about, okay, what's the x component part? Right, you're going to take that value of 9.0 times 10 to the 6 newtons per coulomb, and you're going to multiply it by cosine of 45 degrees, and that's going to give you a value of 6.36 times 10 to the 6 newtons per coulomb, and because this was going there, it's going to be to the left. Okay, and then in terms of the y component, same thing, right, it's that same 9.0 times 10 to the 6 newtons per coulomb multiplied by sine of 45 degrees. It's going to give you the same value because of wonderful unit circle things. So times 10 to the 6 newtons per coulomb, but this one was going down. Okay, so now we're at a point where we have all the x and y components of everything. We just need to actually put them together. So our net field intensity kind of happening here is we first need to figure out, okay, well, what's the sum of my x components? Okay, so we have this one, which was the 6.36 times 10 to the 6 going to the left, and that kind of matched up with our other one that was at D, which was the 2.16 times 10 to the 7 to the right. So it'll be, okay, the one to the right, the 2.16 times 10 to the 7, minus the one going to the left, which was the 6.36 times 10 to the 6. And that gives us an overall to the right value of 1.524 times 10 to the 7. Okay, so that's overall to the right. Then we do the sum of our y components. Okay, so there's the sum of our y components. And again, what we had is we had that one going up, right? So the one that from C, that was the 2.16 times 10 to the 7, and then we had that value then going down, right? So it's actually the exact same values once again, right? Because the one going down was the same as the one going to the right, which was the 2.16 times 10 to the 7. And then the one going down was the same as the one going to the right due to the cos 45. So you get the same value again of 1.524 times 10 to the 7 newtons per coulomb, and overall that's going to be going up. Okay, so you've got your x and your y component, you put it together using your Pythagorean theorem again, so essentially what you have is, the electric thing acting on D. Just need this space. Okay, so, right, if this was our point D, we've got a force acting this way and acting this way. This is our, our net field intensity, okay? We have that both of these values here are the 1.524 times 10 to the 7, 1.524 times 10 to the 7. So this is just now Pythagorean theorem, right? As there, 0.24 times 10 to the 7 squared. Okay, so all of that gets done, and you get this net electric field intensity as a value of 2.0 155 times 10 to the 7 newtons per coulomb. In terms of rounding, sig figs, we only get 2, so really it's 2.2 times 10 to the 7. And then in terms of direction, you need to, again, find this particular angle. Okay, now yes, typically we'd go tan inverse to find that, but just a little basic look at that triangle and you kind of go, well, that's a right angle, these two sides are the same, that must mean that these two angles are equal, so it's got to be a 45. Use the tan inverse if you need to, but it's a 45-degree angle, right? And then we could describe that as 45 degrees counterclockwise from the positive x-axis, right? So CC counterclockwise from positive x-axis, right? Or east 45 degrees north, okay? So there you go. Putting it all together, okay? So what we've got is one last example there. Again, you'll see that here's kind of a layout of the steps in no particular order, really, of how to solve that problem, right? So we had the given information, redrew the diagrams. You could have found that diagonal first. I kind of waited, find the forces acting on point D, which we did, right? Break it up into its vector components, right? To create your right triangle, find the magnitude using Pythagorean theorem, find your angle using tan inverse. Okay, so again, you see all of that work done out on there, but you saw me do it as well. Okay, so last problem for this. Okay, so we've got example problem number 3. This one gets quite mathy, just warning you. But here we go. Okay, so in this one, we have been given that two charges are separated by a distance of exactly 1 meter. If charge A is positive 8 microcoulombs and the charge on B is minus 3 microcoulombs, calculate the point where the net electric field would be 0. Okay, so looking at that diagram, please note that you've got two different types of charges, right? So here, this is our positive charge, and as we talk about with electric fields, that field intensity is radiating outward, okay? Whereas this is a negative charge, so that electric field intensity is pushing inward, okay? So at any point in between these two charges, you're still going to be pulling both in the same direction, okay? And let me just kind of show this to you on the board. Okay, so like I mentioned here, if you've got point A that's positive and its electric field intensity is going to be doing this, right? And over here you have a negative charge and its electric field intensity looks like this, okay? At any point here, right, let's suppose we have a point here, you're going to have a force pulling this way from this one, and it's still going to be pulling that way from the negative charge as well. So any point here in between is still going to just be pulling all to one direction. So it's not going to cancel out. You're not going to get 0, right? So in order for us to actually be able to get a net field intensity of 0, right, you're going to have your positive charge here and your negative charge here, right? Again, this is radiating away from the positive charge. This is pulling in to the negative charge. Your net force of 0 is going to happen somewhere over here where the field intensity from the positive charge will be pulling this way and the field intensity from the negative charge will be pulling this way, and that'll cancel each other out. Okay, so that's what's happening. Now, if both of these were positive, then yes, that net of 0 is going to be somewhere in the middle, right? Because they would have been pointing in opposing directions and canceling each other out. But because this one is negative, we need to go further beyond that 1 meter distance before we get that net field intensity of 0. Okay, so that being said, what you need to look at then is, okay, well, we want our electric field intensity to be 0. Okay, so this is A, this is B, and this is some point C beyond this 1 meter distance. and we don't know how far away that is. So we'll call it x. Okay? So some point x meters away from charge B, we get some point C that's 0, where the net electric field intensity is 0. So then what we've got to deal with then is, okay, well, what would be the actual intensity of the electric field intensity that C experiences from A, and what's going to be the intensity that C experiences from B, right? So what you'd have is, in order for that to be 0, they need to be equal to each other, because this one would be positive and this one would be negative. So what we're looking at is, we want to set up where the electric field intensity, obviously the only absolute value aspect of it, okay, of A on C, we want that to equal the electric field intensity of B on C. Okay? So then, again, we have formulas for this, right? So this is our KQ over R squared, and then this is also KQ over R squared. Thing is we don't actually know the distance between A and C, or B and C, but we know that there's a distance of 1 meter between A and B. So if X is considered the distance away from B, X can go in here. Okay, so this can now become KQ over X squared, and the distance from A all the way to C is that X plus 1. So this is now, so that's QA, that's QB, and this is now going to be X plus 1 squared. Okay, so now we can solve for X, because these are your constants and you know these charges and you can solve. So let's get into that. Right, so using this, right, we've got our Coulomb's constant, that's our 9.0 times 10 to the 9, multiplied by the charge on A, which was a positive 8, but again, we're just dealing with absolute values, so don't worry about the positive or negative, right? That positive or negative was what able to correctly set up the problem, right, of knowing that we had to go beyond point B. Other than that, it's fine. So that was microcoulombs of minus 10 to the 6, and it was divided by this x plus 1 squared, okay, and that is equal to this one here, which is that same 9.0 times 10 to the 9, multiplied by our charge on B, which is 3 microcoulombs, so 3.0 times 10 to the minus 6, all divided by x squared, okay, and we're solving for x, the distance away from point B. So, nice little bit of math, right? We can multiply this, we can multiply this. That gives us a value then of 7.2 times 10 to the 4 divided by x plus 1 squared is equal to 2.7 times 10 to the 4 divided by x squared. Cross multiply here, and I'm actually just going to get rid of the scientific notation to make it easier. So this is just 72,000, right? This is 27,000. So when I multiply that by that, I get 72,000 times x squared, and that's equal to x plus 1 squared times 27,000. Okay, now remember, you would need to expand this x plus 1 squared correctly using binomial expansion, right, going x plus 1 times x plus 1. So when you do that, you get x squared plus 2x plus 1 multiplied by 2,700. Okay, and then you use the distributive property to multiply that 27,000 by each of these 3 terms in here. So what you get is this 72,000 x squared is equal to 27,000 x squared plus 54,000 x plus 27,000. And quadratic, right? So that means we can then bring that all over. How do we solve a quadratic? We set it equal to 0, we factor, or we use the quadratic formula to solve. So at this point, dun, 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 we are now ready to since this one's bigger, I'm going to bring everything over to the left. So 72,000 x squared minus 27,000 x squared. That gives me a value of 45,000 x squared. Bring the 54,000x over, so minus 54,000 x. Bring the constant, so minus 27,000. All equals 0. These numbers are massive. Clearly, they can all be divided by 1,000. So you get 45x squared minus 54x minus 27 equals 0. Those can all be divided by 9. And you can get 5x squared minus 6x minus 3. Quick little look there. Minus 15, add to give you -6. No, not going to factor, so quadratic formula here we come. So x is going to equal then negative b, so it's a positive 6, plus or minus the square root of b squared. So negative 6 squared minus 4 times a, which is 5, times c, which is negative 3, all over 2 times a, so 2 times 5. Okay? I don't need to see any steps beyond that, so just go and calculate that. Remember, you're going to get 2 answers. One answer is x is equal to 1.58 meters. The other one is x is equal to negative 0.38 meters. Okay? However, this we're going to disregard because if we think of that being a negative distance, right, going back to our initial diagram of our 2 charges, x was defined as the distance going beyond point B. So if we have this as negative, it brings it back in here, which we already determined didn't make sense based on the way the field charge directions were working. So we disregard this, and our answer is that the point where the net electric field charge is going to be 0 is 1.5 meters beyond point B. All right? And that's that. Love it when the math comes together. All right? So again, you can see calculations that way as well, but I just did them on the board. And then you've got some practice questions. Okay, so these ones might take you a little bit longer because as you saw with those last couple examples, they do, they do require a bit more math. They do require a bit more setup, right? Just kind of really make sure you're okay with the setup before you go and attempt all of the math, because that'll be a big waste of time, right? So the solutions are there. Check them. If you feel like you've got it set up right before you go and do all of the work to solving, maybe do a quick check there so that you know you're not going to go all the way through the process and then go to check and see if it's wrong, okay? So that's there. All right?